Our next speaker is Yury Makarychev from the Chicago, right?
Yeah.
And here's the title of his talk.
First of all, I would like to thank the organizers for putting together this wonderful workshop and for inviting me. And thanks everybody for coming to my talk. So today I will talk about key means and key medians under dimension reduction. And my talk is based on joint work with Konstantin Makarychev and Ilya Rosenstein. And let me start with defining the problems we are going to talk about today. So we study the Euclidean key means and key medians. In these problems, we are given a data set of points x. So every point in x is a point in a high-dimensional space Rm. We want to partition x into k clusters, C1, etc., Ck, so as to minimize the following objective functions. So for key median, the objective is to minimize the sum over all data points u, the distance between u and the center of the cluster Ci that contains u. And for key means, the objective is very similar, except that we square the distances. These two problems are widely used in practice, in particular in machine learning, in big data, and arguably these are among the mostly used clustering problems, clustering objectives. Yeah?
Ci has to be a data point, or it can...
CIs are, small CIs are arbitrary points in the Euclidean space, so they are not in the data set.
Because your big C's are in data points, so it's a little confusing. Because you said little c in each big C.
Right, that's a type. For each CI, not in each CI, for each CI. This is a type, sorry. Yeah. Any other questions about the problems? So these are the problems we are going to study. Now let's switch gears for a moment and talk about dimension reductions. So a dimension reduction is a random map from a high dimensional space Rm into a much smaller d-dimensional space Rd that approximately preserves distances with high probability. More precisely, we consider a map that preserves the distance between u and v up to a factor of 1 plus epsilon with probability at least 1 minus delta for every u and v. And here, epsilon and delta are the parameters. Dimension reductions were introduced and studied by Johnson and Lindenstrauss in 1984, and they showed that there exists a family of random dimension reductions with dimension equal to log 1 over delta over epsilon squared. And as was relatively recently shown by Larson and Nelson, this dependence of d on delta and epsilon is actually optimal. Dimension reductions are widely used in computer science, in particular for data compression. So if you have a data set in a high dimensional space, we can compress it by applying a dimension reduction. In particular, if we have a data set on n points and the dimension is logarithmic in n, we can, by applying a dimension reduction, we can preserve all of the pairwise distances with high probability. And there is a wide body of literature on dimension reductions, and these are just some papers on the topic. For the purpose of this talk, let's assume that our dimension reduction is based on a random orthogonal projection onto a d-dimensional space or a random Gaussian projection. And now let's get back to our problems, key means and key medians. And so we have a data set in a high dimensional space, and it's natural to do the following. Instead of clustering this data set in a high-dimensional space, let's first project it into a small d-dimensional space, cluster it in the d-dimensional space, and get the desired clustering, which will correspond to a clustering in the high-dimensional space. So this approach was proposed and studied by Boutides et al. Of course, in order for this approach to be meaningful, we want it to preserve the cost of the clustering. So we want the cost of the clustering in the high-dimensional space to be approximately equal to the cost of the clustering in the smaller dimensional space. And ideally, I mean, at a bare minimum, we want the cost of the optimal clustering to be approximately the same, but ideally we want the cost of every clustering to be the same. And then we are guaranteed that when we project our data set into d-dimensional space, find a good clustering in this space, it will correspond to a good clustering in the original space. So let's see for which dimensions d we can get this. So first of all, if the dimension is logarithmic in n, it's easy to see that the cost of every clustering is preserved up to a factor of 1 plus epsilon with high probability. And as a warm-up, we will see how to prove that. Now, Boutides et al., who initiated this line of research, showed that it is sufficient to have dimension k over epsilon squared, and then the cost of the clusterings are preserved up to a factor of 2 plus epsilon. And note that this bound on the dimension does not depend on n. So if k, epsilon, and delta are fixed, and n goes to infinity, then still this dimension remains a constant. So this is very important. Cohn et al. Later improved the result of Boutides et al. And showed that when the dimension is linear in k, the distortion is actually 1 plus epsilon. And further, they show that when the dimension is logarithmic in k, the distortion is at most 9 plus epsilon. In our work, we show that when the dimension is logarithmic in k, the distortion is 1 plus epsilon. And this bound on the dimension is essentially tight because it's easy to see that the dimension must be at least log k over epsilon squared. So in our formula, there is some extra dependence on epsilon. So we have this epsilon, and we don't know whether this epsilon is necessary or not. So up to this epsilon, our bound is optimal. And let me mention that in many applications, k is much, much smaller than n. So say we want to classify some items, then n is the number of items, and k is the number of categories. So it may be, say, logarithmic in n, and then our bound gives log n, while the trivial bound gives log n. Yeah?
This distortion is for the optimal or for all clusters?
For all clusterings. Now let's talk about k-medians. So for k-medians, there were no prior results. Even in contrast to k-means, the log n bound is not obvious for k-medians. It follows, however, from the Kirsch-Brown theorem, and Ravi asked the question, what happens with k-medians here at Simon's at a tutorial talk in August. We show that when the dimension is log k over epsilon squared, then the cost of every clustering is preserved up to a factor of 1 plus epsilon. And again, this bound is essentially optimal up to this epsilon. Do you have any questions about the results?
What is this theorem?
Where is?
What does it say?
Our theorem?
Not Chris Brown's theorem.
Or Kirsch-Brown theorem. So, I mean, okay, it says that we have a, say, one Lipschitz map from a subset of Euclidean space to Euclidean space. We can extend it without increasing the Lipschitz constant. Later on, I will very briefly talk about it, but most likely I will not have to take. I will not have enough time to tell anything kind of meaningful about it. Any other questions? Okay. So this is an overview of my talk. So we will focus mostly on k-means today. And first, we will discuss some of the challenges with the proof. Then as a warm-up, we will see that when the dimension is logarithmic in n, the cost of all of the clusterings are approximately preserved under dimension reduction. Then we will discuss a very important special case. And I can't define it formally now, but loosely speaking, in this special case, all the distorted distances are uniformly distributed inside clusters. So we don't have clusters where there are a lot of distorted distances, but I will, of course, formally define it later on. And then we will see how to remove a small number of the outliers in our data set so that the remaining points satisfy this condition from the special case. And by doing so, we will see that the cost of all points other than outliers is preserved in some sense. And finally, we will see what to do with the outliers. And in the very end of the talk, we will spend a couple of minutes discussing the k-medians problem. So this is our plan for today. Let me now formally state our result. So we are given our data set X. It's a subset of Rm. And we have a random dimension reduction phi from Rm to Rd. We assume that D is at least this quantity. And here, epsilon is the desired distortion, and delta is the failure probability. And we show that with probability at least 1 minus delta, the cost of every cluster in C is approximately preserved up to a factor of 1 plus epsilon. Any questions? Okay. Now let's, yeah.
Probability is uniform over all clusters, or
so with probability, with this probability, no matter what clusters you take, you get this. So with this probability for all clusters simultaneously, this happens, and this is important if we use this in practice, because otherwise maybe we will find some for each specific dimension reduction we will find a bad clustering, and then that's bad. Yeah.
So do the clusterings have to be separated by Warner diagrams, hyperplanes, or any? Can I pick any arbitrary partition?
Any partition, even if it's hugely suboptimal. Yeah.
In k-means, we only care about the special clusters that are given by center points, right? Those are the optimal.
Right, but centers don't have to be. I mean, we prove that for all clusters, right?
Okay, so it's even stronger than what you need, in fact.
Right. Okay. But I agree that in practice, maybe we don't care about all clusters, but still we prove that for all.
It's not just in practice, like, those clusters are the optimal ones for k-means.
Right.
They're based on centers, right? So you don't have to look at all clusters that won't, if they're not based on being the closest to a center, then they're not part of the optimization in a sense.
All right. That's true.
Anyway, it's even stronger. So.
But also, if you have a Voronoi partition in the projection, it doesn't necessarily correspond to a Voronoi projection in the regional space and vice versa. So we should be a little bit careful with that, but basically I agree. So let's see now what the challenges are, and assume for a moment that we want to prove a weaker result. We only want to prove that the cost of the optimal clustering does not decrease much. And it's not hard to prove that if we take the optimal clustering C star, then the cost of C star is approximately equal to the cost of the C star projected. So this is actually pretty easy to show. Now, what is challenging is to prove that there is no other cluster in C prime which is much better under projection. So maybe there is a suboptimal cluster in C prime, but once we project C prime into a low dimensional space, the cost of C prime drastically decreases, or decreases by a factor more than 1 plus epsilon, and now it's considerably better than the optimal clustering. Again, for every specific C prime, it's not hard to prove, but we have exponentially many different clusterings, and the probability that each of them violates this property is, loosely speaking, delta, which does not depend on n, and we may think that it's some constant, okay? So this is a challenge. The challenge is that we have exponentially many different clusterings, and each of them in the projection potentially might be better than the optimal clustering. Okay, now let's assume that D is logarithmic in n, and see why in this case the claim is easy. And here it's very useful for us that we can write the objective function in terms of pairwise distances between points. So we use this formula for the class of clustering C. This is a pretty well-known formula. We just take the sum of all pairwise distances inside of each cluster, and we normalize it appropriately. Now, if the dimension is logarithmic in n, then all pairwise distances between the points in X are approximately preserved up to 1 plus epsilon. Therefore, all these terms are approximately preserved, and we get that the cost of every clustering is approximately preserved. Now, this approach does not work when the dimension is logarithmic in K, because each term is significantly distorted with a constant probability, with a small constant probability delta. So we will have many terms that are distorted. And we need somehow to take care of these kind of distorted terms. Now let me introduce some notation. Yeah?
So the cost is this sum of within cluster distances, is that right?
So one way to define it is the distance between the points and the center squared, but another way is to use this formula.
It occurs to me that the distances in high dimensional space are larger than the ones in the low dimensional space, right?
When we project, we also kind of renormalize. Okay. So we assume that all this, in expectation, the distance doesn't change. Any other questions?
So if you put all the points just on one center, which would be a very bad thing to do, with this, all the within cluster distances are all 0. So would that be a very low cost, or?
If what?
What if you give it a very trivial? What if the embedding or the projection puts all the points just together in one point?
Yeah, that will be bad.
Would that show up badly in this cost?
The cost will go down significantly. Yeah, I mean, if you project everything into one point, then the cost from some positive number will go down to 0. So
wouldn't
then
that mean by the way that you're measuring the cost, wouldn't that be a good k-means then?
Oh, right, but we don't want it to change. We don't want, it's also bad for us if in the original instance the cost of the clustering is high, but once we project it, the cost is low. Then, we don't preserve the objective function. So that's not good for us.
Oh, I see. Okay.
I wonder if there's a clarification order. This formula isn't absolutely correct. It has nothing to do with it. So the cost as originally defined is just equal to this.
Okay.
Yeah, these two costs are just
Does that
equal.
address your question? Maybe.
Okay.
I don't know.
Okay. Yes.
Any other questions? Okay, let me introduce some notation. So for every specific projection phi, let call this clustering C1, etc., Ck to be the most distorted clustering. So kind of the worst clustering for this specific projection, for this dimension reduction. Then the C is a random clustering because phi is random, and you may assume that the C is simply a function of the random projection. And we want to prove that the cost of this most distorted clustering C is approximately preserved under dimension reduction with high probability. And also, let's say that the distance between U and V is 1 plus epsilon preserved if we have this approximate equality. And if this approximate equality does not hold, we say that the distance is distorted. And also, we will think that the parameter delta is polynomial small in 1 over k and epsilon. So it's sufficiently small, but still, when k and epsilon are fixed, this is a constant. So in particular, delta, of course, does not depend on n. But it will be, we will need that it's pretty small. Okay, since we are particularly interested in the terms in the expression for the cost that are not preserved, let's introduce the distortion graph. In the distortion graph, we can so the distortion graph is the graph on the set of data points, and 2 points U and V are connected with an edge if the distance between them is distorted. So this is a random graph, so it depends on the dimension reduction, on the random dimension reduction. Now, the good news is that every edge is present in this graph with probability at most delta. This is guaranteed by our property that our map is a dimension reduction. The bad news is that delta is not very small. In particular, it doesn't depend on n. So in some sense, a constant fraction of all the edges are present. Also, the bad news is that edges are not independent of this graph, and the clustering C depends on the dimension reduction, and in particular on the set of the distorted edges. In particular, our graph may have high degree vertices. So it may happen that many distances from a specific point are distorted. It may also happen that we have a small cluster and all or most of the distances inside of this cluster are distorted. So in a sense, this is pretty bad news for us, because then the cost of this cluster is not preserved, right? So it may, even though we are going to prove that the cost of the clustering is approximately preserved, it's not true that the cost of every cluster is approximately preserved. At least when we talk about a multiplicative distortion. Okay, now let's analyze the problem using the distortion graph. So as we know, the cost of every cluster Ci is given by this formula. Now, if U and V are not connected with an edge, so if the distance between U and V is approximately preserved, then this term is distorted up to 1 plus epsilon. And so basically there is no difference. I mean, the amount this term contributes to the original problem and to the projected problem is the same. We don't have any issues with this term. And what we need to do, we need to take care of the terms for the edges, for the distorted distances. And what we are going to prove, that if we add up all these terms over edges in the original instance and in the projected instance, then they differ by at most some epsilon prime times the cost of the clustering C. And epsilon prime here will be pretty small, maybe of order epsilon over k. Okay? What is important that we get this this approximate equality up to some additive error. So we cannot have a multiplicative error here, because in particular it may happen that one of these sums is very close to 0 and the other is not. Okay? So this is our plan. And first, let's consider a special but very important case where all vertices have low degrees in their clusters. So let's assume that every vertex in our graph is connected to few vertices in its cluster. More precisely, what we require that if we take every vertex u in a cluster Ci, then it is connected to at most some 1 minus theta fraction of other vertices in the same cluster. Okay? Note that this bound on the degree depends on the cluster. So if you have a large cluster, the bound is larger. If you have a small cluster, then the bound on the degree is smaller, because we consider only its neighbors in the cluster, and and the number of neighbors should be at most. It should be not 1 minus theta. It should be a theta fraction. So it should be theta, a theta fraction of all vertices in the cluster. Okay. So let's assume that this happens, and now we are going to bound all terms u minus v squared. Again, we don't have any issue with non-edges. So for every non-edge, the term is approximately preserved. We are going to show that the contribution of terms for edges is small, and therefore we can essentially ignore it. So let's consider an edge uv such that u and v belong to Ci, and let's take an arbitrary point w in Ci. Then by the triangle inequality, we have this, and by squaring it, we get this inequality. Now, let's choose w uniformly at random inside cluster Ci. Okay? And then, when we do this, each term will be selected at most 2 delta times in expectation. So every term will be selected pretty rarely, and from that we get that the sum of u minus v squared over all edges is at most 8 delta times the sum over all u and v in the cluster. Okay? And note that this expression is the cost of the cluster. And A delta is very small. So what we see is that the contribution of these terms corresponding to the distorted edges is very small comparing to the total cost of the cluster. And essentially we can ignore it.
Where does data come from? Where does delta come from?
Okay, it should be.
Is that theta?
It should be theta, right? It should be theta. So it should be theta here. So here we use that every vertex is connected with at most theta neighbors inside its cluster. So we reroute sort of a theta fraction of the edges. And here it's important that this bound on the degree is uniform. Any questions? So okay, what we just showed that the cost of the cluster is approximately equal to the sum over all non-edges. We know that the value of the sum is approximately preserved under dimension reduction. So we have this approximate equality, and again, for using the same argument, we know that this sum is approximately equal to this sum. So we see that if this special property is satisfied, then the cost of the clustering is approximately preserved. But in general, of course, we cannot assume that this property, special property, holds, in particular because our clustering depends on the distortion graph. Let's try the following. Let's try to remove a small set of the outliers from our instance so that the remaining instance satisfies the desired property. So this is what we want to do. We first get the random dimension reduction. It defines the distortion graph, we also get a clustering which depends on the dimension reduction. In this clustering, there may be high degree vertices like this vertex. We may have even very dense clusters, or potentially a cluster may be a clique. We remove a small number of the outliers. So here they are represented as black vertices, and in the obtained instance, all vertices have small degrees. So we use the previous argument. Formally, we want to remove the outliers and obtain a subset X prime, which we call the non-distorted core, so that the following two properties hold. First of all, edges are sparse in the obtained clusters. So basically, the special property that we talked about holds for the remaining clusters. And the second property is that outliers are rare. So the probability that U is an outlier is at most theta. Okay, and let me stress that the set of the outliers does depend on the random dimension reduction. So it's a random set. Let's see how we find these outliers. And let's first assume that all clusters are large. So all clusters of size n over k approximately. And let theta be, loosely speaking, delta to the power of 1/4. Let's remove all vertices of high degree from our graph. So more precisely, all vertices of degree at least theta n over k. And then the remaining vertices have degree less than theta n over k. So since the size of every cluster is approximately n over k, this means that every vertex is connected to at most a theta fraction of the original cluster. Now, simply because every edge is distorted with probability, every distance is distorted with probability delta, the expected degree of every vertex is at most delta n, and applying Markov's inequality, we get that it's highly unlikely that a vertex has degree greater than this. And so we remove every vertex with a small probability less than theta. And finally, since we remove every vertex with a very small probability, it's likely that we will remove a very small fraction of the vertices. And because of that, it's unlikely that any cluster will significantly shrink. And because of that, not only the degree of every vertex is at most theta times the size of the cluster, times the original size of the cluster, it's also at most theta, or maybe 2 theta times the size of the new cluster after we remove the outliers. So in this case, so if all the clusters are large, the analysis is simple. But in general, this is not given. Some clusters can be small, and then this analysis doesn't go through. In particular, it's not sufficient to remove vertices of degree at least theta n over k, because a cluster can be much smaller than n over k. And also, when we remove outliers, it may happen that we will remove most vertices from the cluster. And then again, this argument will not go through. Yeah.
5 minutes.
And loosely speaking, our idea is as follows. We want to assign weights to the points so that with respect to these weights, every cluster is heavy. And then we will essentially reduce the analysis to the previous case. More formally, we prove the following combinatorial lemma. So we prove that there is a measure mu on X and the random set of new outliers R, so that after we remove these outliers from R, the measure of every point is greater than 1 over the size of the new cluster. This means that all points are sort of heavy. We also have this condition that says that the total weight of all points is relatively small, so it's bounded by a polynomial in k and theta, and that we remove every point with small probability. So I don't want to talk about this in any detail, so this is a pretty technical lemma and pretty technical analysis, but basically using this lemma we can reduce the general case to the case where all clusters are of approximately the same size. So using these techniques we can take care of all points other than outliers. So now let's see what we do with the outliers. So suppose that we have a cluster and we have these black points that are outliers. We need to analyze the contribution of edges between outliers and edges between outliers and non-outliers. The analysis is a bit different, but let's look what happens with these edges. So let's assume that U is an outlier and V is not. And let's consider a fixed optimal clustering of X. So this clustering C1 star, etc., Ck star. And let C star, this point C star, be the optimal center for U in this clustering. So we write the triangle inequality for U minus V. So U minus V is equal to V minus C star to this distance up to this term, the distance between U and C star. So we have this approximate equality. We have the same approximate equality in the projection. Now, when we define the non-distorted core, we may actually assume that all distances from the points in the core to optimal centers are approximately preserved. And we can do that because there are only k optimal centers. So with a reasonable probability, the distance from every point to all these k centers is preserved. And if we remove extra outliers, those points for which the distance to one of the optimal centers is not preserved, we will essentially get the same analysis. So we have this approximate equality. And now we want to show that the total contribution of these terms and these terms is small. So let's take care of these terms, C star minus U. So what we do, we add these terms up over all points U that are outliers. And now we know that every point is an outlier with a small probability. So simply by the linearity of expectation, we have this bound. It's theta, the probability that U is an outlier, times this expression. And this expression is the optimal cost. So we get that the total contribution of all these terms is at most theta times opt. Now, the analysis of the total contribution of these terms is more involved because the event that U is an outlier depends on phi, so we don't have independence here, but we still show that the contribution of these terms is small. And also there is another technical issue here, that we have these triangle inequalities for Euclidean distances, and in the objective we have squared Euclidean distances, so that adds some work, but it's possible to take care of that, and this basically concludes the proof. Let me
1 minute.
finally say a word about key medians. So for key medians, the problem is more difficult because we don't have a simple formula that expresses the cost in terms of pairwise distances. So we have to consider the optimal centers, and that complicates things significantly. So to solve this problem, we prove a robust version of the Kirsch-Brown theorem that I mentioned, and using the techniques I just described and the Kirsch-Brown theorem, we are able to get our result for k-medians. And in summary, let me tell you what we did. So we proved that the cost of every clustering is preserved when the dimension is logarithmic in k. Our result applies to k-means, k-medians, and more generally to any sort of Euclidean k-clustering with the LP objective. And I'll be happy to tell you more about this offline. And in particular, our result for k-means answers an open problem by Cohen et al. Thank you. Any questions? Yeah.
So, I'm just thinking about approximation algorithms for finding k-means clustering. So I don't really know what's the state of the art. Is there something known that's polynomial in all n, d, k, and 1 over epsilon?
We cannot. So the.
Approximation, not exactly.
No, there is an approximation algorithm, but we cannot solve the problem in polynomial time in n, k, and 1 over epsilon.
Is there, maybe there's an application of this? I don't know.
But many algorithms, if we have an algorithm, even an approximation algorithm, and we project our data set in a low dimensional space, then the algorithm will work faster.
Yeah.
So this is probably one of the main applications. And we will need much less memory. So potentially the algorithm may also give a better approximation guarantee, but I don't know if it's necessarily the case.
All right, let's thank Yury again. So we're coming back at 11:40.